In this video, I will share a topic on electric field. Qualitatively, electric field is three-dimensional space around a source charge within which its effect can be experienced by a test charge. Suppose we have a source charge Q. Surrounding it, there is some space in three dimension. If I introduce some test charge within this space, this test charge will experience an electrostatic force due to this source charge. So this space is called electric field. Now the question is, what is the intensity of electric field within this? At every point within the electric field, intensity of electric field will be different. In order to define intensity of electric field at a point, we write E is equal to F divided by Q naught. Means if F is the force experienced by test charge Q naught due to this source charge, if I divide this force by test charge, it will give us force per unit test charge. The condition is test charge must be very small. It must approach zero. Means its presence must not affect the position of source charge. Second condition is Q naught must be positive in nature. Test charge is always taken as positive. So this is the definition of electric field. Again, let me revise. Electric field at a point P due to a source charge is defined as electrostatic force experienced by a unit positive test charge, means per unit test charge. In vector form, I can write the same relation as E vector is equal to F vector divided by Q naught. Means direction of electric field will be same as that of electrostatic force. Test charge is always taken as positive. Depending on the nature of source charge, direction of force can be decided. That direction will be the direction of electric field. Now let us come to the units of electric field. In SI units, electric field is measured as Newton Coulomb minus 1. It is clear from this definition of electric field. And in CGS system of units, we can write dyne strat coulomb minus 1. Okay. So these are the units of electric field. Now I will derive a relation for electric field. Electric field due to a point source charge. I will make use of the definition earlier I have given. For this purpose, let's draw a diagram. Suppose this is a coordinate system in which source charge is placed here. Its position vector is r vector and test charge is placed within its electric field at any point. Let's suppose position vector of test charge is r naught vector. As we know from Coulomb law, force experienced by test charge can be written as 1 upon 4 pi epsilon naught Q naught upon r naught minus r vector mod q multiplied with r naught vector minus r vector. If I take Q naught to left hand side, I get answer for electric field. So electric field will come out to be 1 upon 4 pi epsilon naught q r naught vector minus r vector divided by r naught vector minus r vector mod q. So this is the complete relation for electric field due to a point source charge, where source charge has position vector r vector and test charge, that is point of observation P, has position vector r naught vector. Now let us take a special case in which source charge lies at origin of coordinate system. Let me again draw the diagram. This is coordinate system, x-axis, y-axis, z-axis. If our source charge lies at origin, that is q is here, and test charge at the same position vector r naught vector, because source charge is coinciding with the origin, so its position vector will become 0. So we can write in this case r vector is equal to 0. Using this value in previous result, I can write electric field at this point of observation P is equal to 1 upon 4 pi epsilon naught q upon r naught magnitude cube multiplied with r naught vector. I have obtained this by putting r vector is equal to 0. This is the special case. This result can be modified as E vector is equal to 1 upon 4 pi epsilon naught q upon r naught magnitude square multiplied with r vector upon r naught vector mod. I have just taken one r naught vector mod over r vector. Now this ratio is nothing but unit vector. So I can write E vector is equal to 1 upon 4 pi epsilon naught q upon r naught magnitude square r naught cap. This is special relation when source charge lies at origin. We know that any vector can be written as its magnitude multiplied by its unit vector. If I compare the previous relation for electric field with this, I can write magnitude of electric field due to point source charge in the special case as 1 upon 4 pi epsilon naught q upon r naught magnitude square, or I can write E is equal to 1 upon 4 pi epsilon naught q upon r naught square. In this result, r naught represents the distance between source charge and test charge. R naught is distance between source charge and test charge. If we know the distance, by putting the value of that distance and the value of source charge, we can find electric field at the point of observation by using this relation. That's all.